In this video, I'm going to be showing you how to solve this really interesting integral involving floor functions and everything that I found on dailyintegral.com on December 10, 2025. So here's our problem on screen, and at first glance, it will be really nice to make a substitution now that we see the only terms involving x are all going to be the floor function of 1 over x. So we set u equal to that. In order to write dx in terms of du, we need the derivative. First, let's visualize the graph of the floor function in general. And no matter what's inside the floor function, it's always going to be a bunch of horizontal lines. So whenever the function is differentiable, the derivative is always going to be 0. So we write du over dx equals 0. We can then rearrange the terms to get dx is equal to du over 0, but we run into an issue. When we try to substitute that in, we end up dividing by 0, which gives us a problem. So it turns out we really can't use the substitution, so away it goes. But we can actually substitute just the inside of the floor function and deal with it later. Let's set u equals 1 over x. So we can rearrange these terms, differentiate both sides, and we are left with this expression over here. Now let's change the limits of integration. We start with 0 plus to 1 and plug it in to 1 over x. That becomes infinity to 1. Reverse the limits of integration to the right order and get rid of the negative sign. And we are left with this integral right here. Now, we can actually apply a really cool property of the floor function. So first of all, note that the floor function is basically like a piecewise function, composed of a bunch of constant functions. So between any two consecutive integers, it's basically a constant, and it's always going to be equal to the lower limit. In order to use this property, we can actually break up the integral's limits into integer intervals. So that's going to look something like this, with the limits going from 1 to 2, 2 to 3, 3 to 4, blah blah blah, so on and so forth. We can then write this in sigma notation, and it's going to look something like this. Alright, next, we can move the integral in front of the constant term that only involves n. Taking the antiderivative and evaluating the integral, we're left with a single fraction, which now we can easily see there's a really nice cancellation of terms. Just cross that out, and we're left with a much simpler expression. Now, we can write out the series and factor out a negative sign. Note that the inside of the parentheses looks really familiar here. Some of you may know that this is what you call the Leibniz formula for pi, which evaluates to pi over 4. But in reality, you don't need to memorize this identity. You can also recognize this as the Taylor-Maclaurin series of the inverse tangent, where the argument is 1, because you can see the numerator is always 1, and the denominator corresponds with the summation formula. The inverse tangent of 1 is pi over 4, and we can plug that in, take its negative, giving us our final answer of negative pi over 4. And we're done.